Thank you.
Great, thanks. All right, so welcome back. So I'm going to start off this next part where I have three kind of topics that I want to cover. One is a little bit on classification, pretty brief. Then something on reinforcement learning, which is sort of a model-free kind of approach to doing optimal control. And then coming to mean field games with latent processes that tying back to the whole HMM things. But again, this is just going to be tasters, so not too much details. Okay, so classification problems. This is another generic problem that you see in machine learning, that there are many, many different approaches for it. We're going to look at just two types of classifier, Bayes classifier and multi-class logistic regression. Yeah?
You might want to mention that the presentation is going to be available.
Oh, yes. OK. I will be making all of these slides available, like posting them on my website. And there will be a link from the conference site or from IMPA somehow, or an email to the location. So you can all look at this.
The link is actually on the page of the conference.
Yeah.
There's a link for the presentations that people have already contributed, and for the mini courses that will be available.
Great. Okay. Good. Excellent. Okay, so here we go. So the classification problem. What is it generically? It's simply this. You have a collection of observations. So x's and y's. X's are features. They just represent, in the context of, say, these prices, it could be price and order and balance. That could be a feature. And y would be a classification. So, for example, you can use maybe the previous price change, the previous order imbalance, and the classification is the next price change positive, negative, or zero? That would be a three-class classification with the features price change and order imbalance. So the x's, you have a bunch of pairs of observations, these features, and the class. So it's labeled data as opposed to unsupervised stuff. We're not doing unsupervised learning. This is a supervised, what you classify as supervised learning. And the classes we're thinking of is coming some discrete set, so up to k. And these are the ideas. We're going to try to find some rule that maps you from your feature space, which is script x there, chi, looks like, mapped into the classification set y. That's the generic problem that we want to solve. And there's some performance criteria that we're going to use in order to come up with the different classifiers. So the two types of models that are often used are what are called generative classifiers or discriminative classifiers. And the difference is exactly as you see there. There's two ways you can model classifiers. Either you specify the probability of, say, if you have a particular class, where in feature space is this class likely to appear? That's called the generative model. So you're modeling the probability of x conditional on y. Then you can do the flip side, and instead you can say, okay, at this point in feature space, what is the probability that a class is observed? It's the exact dual. And certain models focus on the discriminative approach, and certain models focus on the generative approach. So we're going to see both of them. So the Bayes classifier. This is the first one we're going to look at. To define it, what we look at is, first of all, define something called the true error. So this is the probability that your classification function h, based on the data that you've observed, is not y. That's the error, right? That's the probability that the classification function that you've created does not equal the correct class. What is the probability of that? That's the true error. And instead, you can't know what that function is. Instead, you're simply going to try to minimize the training error. So the probability of this probability is simply summing up all the events in which your classifier misclassifies and then averaging. This is our training error rate. And what we'll do is we're going to try to, as I said, try to minimize that thing. Or alternatively, maximize the probability that you classify things correctly. So here's the setup. We're going to model, notice that this here is of the generative type. Okay, remember there are these two different, discriminative type. We have discriminative and generative classes. We're conditioning on x being at a point in space, the probability that we have a particular class at that point in space. And you can write that simply as the product of the density associated with being at a point in feature space, conditional in the class, times the probability of a class. Okay? And then normalized. So that's how you can write out, this is just using basic conditional probability definition. And x is, I'm assuming the feature space is here as continuous. Okay? So it's a continuous feature space. That's why we're multiplying by the density of x given that y is little y, and then normalizing. So the Bayes classification rule is simply this. It's to say the classifier is, at some point in feature space, the class that maximizes the probability of observing that class there given the data you see. This, as it says here, maximizes the class that class is observed at that point in feature space. And of course, if you look at this formula, well, the denominator doesn't depend on y, so we can just get rid of it. It's the same thing as maximizing the product of the density times this probability of observing a class. Now, so then the question is, well, how do you model this? And can you do this in a model-free manner in some way? Well, the probability that the class is of a particular type, that's kind of easy. This is an unconditional probability. So based on your data, you simply count. You say, OK, I have a whole bunch of data. They're all over points in feature space everywhere. In fact, it's probably a good idea to have a diagram here at the same time. So we have our feature space. This is x1, x2. We have maybe that's, I've shown a collection of data points. There are two classes here, the x's and the dots. And if you simply count the number of x's divided by the total number of x's and dots, that's an unbiased estimator of the probability that we observe class X. And if I count the number of dots divided by the total number of dots and x's, that's the unbiased estimator of the probability that I observe a dot. So that's what this is saying. We have an easy way to estimate the probability that a class is of a particular type, just from the data. So that's the easy thing, this one. This is not the easy thing. That's where some modeling needs to be done. We now need to specify a priori what is a good model for the probability that if I observe a particular class, that we are at a particular point in feature space. So the Bayes classifier, or actually this is not the Bayes classifier yet. This is a variant of the Bayes classifier. There's also one where you don't make this specific assumption. It's more of an empirical kernel estimator of the distribution. But this version, what you do is you simply say the distribution of the random variable corresponding to the points in feature space given your class is normal with some mean and some covariance structure. And that mean and covariance structure depend on the class. So it's an assumption. Right? It's some basic kind of fairly naive assumption. So we say, if we look at this, for example, you might be tempted to think, OK, if the distribution was normally distributed and with some variance-covariance structure, perhaps the x's are sort of like that in this region, and perhaps the dots have a Gaussian that looks something like that. Okay? I'm drawing the contour plots of the conditional distribution of the points in feature space given that we observe a class of type X or given that we observe a class of type dot. So this is the generic form. So then we say if you look at this classifier, under that assumption, this classifier becomes also pretty simple because this is just it's a multivariate normal distribution, and you can compute. You don't even have to look at the exponential part. You can just take everything out of the exponential, sum up the various terms, and you end up with this basic argmax problem that you have to solve. So you're given a point in feature space. You look at the distance to the kth class over here and here, the kth covariance matrix, inverting it, and then you have this log of the determinant of that matrix. This comes from the density of the normal. And then you also have the log probability of being in a particular class. And you simply need to find the k that maximizes this. Now, if you look at that, this is a quadratic form. So you're actually just looking at intersections of quadratic forms in this feature space. And certain k will maximize that. Just as I've drawn these kind of circles here, you'll see, you can probably imagine that in this region, or maybe in all of the shaded region here, this Gaussian has higher probability of occurring. So you'd call all of those points will be classified as x, as the feature space would classify them as x. And somehow over here along this lower boundary below this curve are going to be the dot class. So it splits the space into these two pieces for this case of just two classes, of two types of classes as an input variable. And of course, there's some sort of quadratic function that makes these, that cuts the boundaries. That's why this is sometimes called quadratic discriminant analysis. So even though it's just the name comes from the fact that this thing is a quadratic function here. So they call it quadratic discriminant analysis. And then the final question is, well, okay, that's the function that I'm going to use as my classifier. How do I estimate these sigmas and mu's? Well, the idea is, again, pretty simple, pretty straightforward. Given these labeled data like that, well, I could simply look at all data that's labeled as dot, take those points in feature space, and look at the empirical mean, look at the empirical covariance matrix from that, and that's an estimator of the parameters that I would put into my classification algorithm. So you just do that. Just take mu hat and sigma hat, sum them up, but only those that are in the class K, sum them up, only those that are in class K, take those averages, and that sets up our class. So here's examples of this in action. So it's a pretty simple idea. So this is showing 3 classes that I've generated random data. So it's the same. I've made an assumption for the generating data process, if you want to call it that, and I've made 4 simulations of it, and then re-estimated the boundaries in each different 4 simulations. But the boundaries, this is to illustrate, the boundaries are always, they're not always the same, right? If I have this, even if the same data generating process is there, but they're approximately the same. And it gives you some reasonable, rational slices between the data. So you can see the green and the blue and the black are reasonably separated by those boundaries. Similarly, in each one of those different scenarios or simulations. Here, I've changed something about them. You can see that in each panel, I've changed one aspect or another of the data. In the bottom right panel, you can see I've made the green, blue, and black become much more concentrated. Right? And it's separate, again, the boundaries separate them really well. In the top left, I think the blue and the green are much wider spread than they were in the previous pattern. So the boundaries are a little less accurate at separating the data. But that's an example of what we observe. Okay, so now that you have the basic idea of the Bayes classifier, let's take a look at how it works on actual data, not just made up stuff. So this here, I'm using 2 features from this intraday trading. On the horizontal axis is order flow, so it's the buys minus sells. Okay, so the buy market order execution subtracts sell market order execution, but then I transform it, I normalize it. So you subtract its mean and divide by the standard deviation. So this is something that's often done with data of any type that you feed into machine learning algorithms of some kind. It's always a good idea to first standardize your data. The vertical axis is imbalance. Now, imbalance is between -1 and 1, so it's not a good idea to simply standardize it because it has this hard bound. So what I've done is I've used sort of a logic transformation on it. So remember, rho is in the interval -1 to 1. So if I add 1 plus 2, 1 plus rho over 2, then let's call that that's going to be x2, I guess, in this plot. This is now in the interval 0 to 1. Actually, it's not x2 yet. That's, let's call it L2. And then I simply write L2 equals 1 plus e to the minus x2 minus 1. So this is a logit type transformation. I find the x2 that satisfies this. This is always between 0 and 1. This x2 is now minus infinity to infinity. Okay. And that gives me the vertical axis. So sometimes you have to do these little feature selection process, sort of trying to figure out what is the right transformation to make your data fall into the correct framework of the underlying assumptions for the classification algorithm. In this case, the underlying assumption for classification algorithm is conditional on a feature, conditional on a class, your feature is normally distributed. So using minus 1 to 1 is a bad idea. Right? Doing this transformation now makes it useful. So these are 1, 2, 3, 4, 6 different stocks here, and I'm classifying order imbalance and order flow over 1 second, and then I'm looking at the price change in the following second. Okay, so I looked at order imbalance and order flow in a given second, and then the price change is the class. Is it positive? Is it negative? Or is it 0? It's hard to see in the plots because the colors are very similar. There are supposed to be black dots in there, which are the 0 price changes, and then there are sort of cyan and blue dots. They don't show up too well in the screen there. I can see them better here. And there are clearly 3 regions in all of these 3 colors that are shaded. Those correspond to the 3 different classification regions that the methodology picked out. And you can see that it makes sense. There's this band generally in the middle, right, that goes from the top down. That band in the middle is what the classifier says you should have no price change here. So this says if there's very little order flow, no matter what the imbalance was, it's likely that you shouldn't see a price change. Okay. However, if you look at, say, this diagram here, it says if you have positive order flow and there's positive imbalance, then it's likely you would have a positive price change. However, if you have positive order flow and imbalance is significantly negative enough, you may get a negative price change. Same thing over here. If you have negative order flow and negative imbalance, then it's likely you get a negative price change. But if order imbalance is high enough, you can get a positive price change, even if you had negative order flow. So that's an interesting thing. That's showing that there's some interaction between the order flow and imbalance that comes out of this classification engine. And you might say, well, there's some funky things going on here, right? Like this is turning over and so on. That's curving out. That's because, of course, we have quadratic boundaries between everything. But the likelihood of getting events out here are very, very low. Right? There are very few data points out here, which is why I wouldn't even trust necessarily the exact boundaries there. But this is kind of consistent across the board. There's sort of a horizontal line going this way that's tilting and showing you that order imbalance can push the price one way or another. It's not only driven by order flow, and vice versa. Okay, so then we can look at more refinements of this. This is the same data, but now I've put 5 classes. I've said either there's no price change, there's a price change of 1 or minus 1, or there's a price change of 2 or minus 2 or larger, okay, in terms of ticks. And then we redo the analysis. Yeah, Antonio. This is 1 second, so it's asking about I think the timing, the window that I'm using for estimating the data. Yeah, so it's based on 1 second data, and but I haven't tried to look at it on a much longer time scale than that. No, yeah, I mean, like I said, I caveat all of the data stuff that I show as these are just fun little experiments that I've done, and I fully encourage anyone to take these little ideas and then run with them. Yeah. Yes?
This price movement that you are It's measured by the micro price versus the initial price. How are you
Yeah.
measuring?
The question is about how am I measuring the price changes that's occurring here. Let me make it crystal clear. So I have a bunch of 1 second time windows, right? In this second, I look at order flow and I look at imbalance, okay? And then I look at the price change 1 step ahead, measured as a change in the mid price, okay? Oh, I was wondering what happened with my thing. Okay. Yes. So it's changing of it's order flow and imbalance, and then change of mid price 1 step ahead. So it's kind of it is building in the prediction into it. You could, of course, do this contemporaneously, right? You could look at the price change here as something that you're trying to see if there's a good signal from order flow and imbalance. And of course, it will be stronger. It'll be even stronger because if it's during the same period, you'd expect order flow and imbalance to have an influence on the change of price over that same window. But if you do order flow and imbalance in one period and then ask about what does this affect 1 period later, it's not clear that it would have as much of an effect, but it does, at least on this time scale. And as Antonio was asking earlier, it would be good to look at it on different time scales. Yeah. Okay, so this is the case where we have 5 different regimes, as I mentioned. And you can see that there's a lot more interesting structure, particularly from this one here, LBTYK. It's a very interesting structure. So this is 0 price changes in here. The sort of orange and light blue is +1 or -1 price changes. And then the blue, the deep blue and the red are +2, -2 or larger, or sorry, +2 and -2 and larger. So it really splits the regime up into some more refinements. And again, you can use this clearly to generate some strategy. Okay, so that's that. The next thing that I wanted to talk about is there's this, as I mentioned, the Bayes classification. There's a Bayes classification methodology using these multivariate normals to give you the distribution in feature space. So remember here, we assume that fx conditional on y equals y of x is multivariate normal. But this may not be a good assumption, actually, for your data. Maybe the data is too sparse, or it's kind of concentrated here and then concentrated over here as well for one fixed class. Maybe it's sort of dumbbell shape. So how do you go about and incorporating something like that? One very simple idea is instead of using multinormals for this density, you instead use a kernel density approach. So what you do, what's done in this approach is each dimension is kind of viewed as independent of every other dimension. Okay? So that's why I have a product of these little single univariate densities. And each of these univariate densities are kernel density estimator in that feature. So what is a kernel density estimator? It just says, if I have a bunch of observations of data, I simply put a small Gaussian, that's one way to do it, around the location of every single data point. And then you add them up. So this will give you distributions that are kind of, they have lots of valleys and hills in them, right? Depending on where the data points are. And then you might ask, well, how do you pick the bandwidth? The bandwidth is how large of a Gaussian? How much variance do you include in every little Gaussian? There's all sorts of cross-validation techniques that you can use. So you can just sort of remove and add, or take 80% of your data, calibrate it to this, tune your parameter, do the prediction on the ones that you excluded, and repeat, and then you can eventually find an optimal choice for the bandwidth parameter. And that's what's often done in this way, in this methodology. I haven't actually implemented it on that data set that we saw there. But what I have done is I've done this next methodology, this multi-class logistic regression. This looks at the other approach for modeling. So here what we're doing is instead of instead of modeling the probability of the distribution of points in feature space given a class, you model the probability that you are in a class given a point in feature space. Remember, I told you there are two different approaches, right, to doing classification. So here, this model is, if you look at it, it looks kind of like Boltzmann weights. You're taking the exponential of a weight vector dot your data, and then normalizing. And this weight vector depends on your class. This is kind of like the baby version of things that are built into deep learning models and that are built into multi-layer perceptrons, which are part of all of this sort of artificial neural net underpinnings. They're really built off of something very, very much like this. So here you have, as I said, the parameters. Here the parameters are the mean and variance of this multivariate normal. Here the parameters are this weight matrix. Okay, you have a weight vector for every class, so altogether you have a weight matrix. And as I said there, this is really just generalized logistic model, right? In logistic regression, you have a probability associated with a 0 or 1 event, and the features are multiplied by a weight vector, and then you put it through this logit function, which is exactly like that, in order for you to get the probability that you have a particular class. Here, since we have multi-class, this is the natural generalization of it. So then you can ask, okay, how do we go ahead and maximize this thing? So as before, we're trying to find the argmax over our class of the probability of y given x, but this is exactly what we're modeling. And if you look at this, it actually is really simple. What maximizes this, the denominator is irrelevant. E to the something, if I maximize it, is the same as maximizing what's in the exponential. So that's just this. And then the question is, well, okay, if I'm maximizing that, this is a linear function. We have a whole bunch of linear functions that are intersecting, so you just get linear decision boundaries here, as opposed to with the first approach, we got quadratic boundaries. You still need to estimate those W's, right? I haven't told you how do you estimate them. We simply said, suppose we have it, this is what our data is generated, this is how we classify. So then how do you estimate the parameters? It's by using maximum likelihood. So this is going to tie into somewhat like what we had before. So if you take the probability of your data given the model parameters, you're trying to maximize that thing. For this collection of data of classes and points in feature space, we're simply maximizing the probability that a class occurs at that point in feature space that we've observed. And if you write down this probability and take their product, you end up with the log likelihood being this. Okay? So it should look like something that makes sense, right? You have log of the sum over the classes there, and then you have these y's because you want to make sure, remember this probability here is logistic, so you have a 0, 1 event. That's what this W matrix is doing, or sorry, that's what this Y matrix is doing for you. Gives you a 0, 1 wherever you have a class of a particular type showing up at a point in your data, and you need to maximize that. That's not analytically tractable. Right? You cannot maximize this over W's in analytical closed form. So how do you do it? This is another technique that shows up a lot in this machine learning world. It's using, basically, it's doing steepest descent. Okay? That's all it's doing. And you're going to try to find some improvement based on your old parameters that move in the direction of the gradient of your log likelihood. Okay? So that's all you need to do, is you need to compute this thing. And then you just repeat using this methodology. So there's some way to write this down in a closed form. And again, I don't want to go into details. Let's just look at some results. These are the classifications you get here. And let me see by a show of hands. Who thinks this is a better classification than the last one? I wonder if I can show them at the same time. I probably can. Let's see. If I do that and open it again with a different PDF viewer. Okay. Who votes for the left? No one.
So the problem
Vote.
is exactly the same.
Exact same data set. One is using logistic, multi-class logistic, and the other is using the Bayes classifier.
Colors mean the same thing.
Colors mean the same thing. Colors mean the same thing. So colors are, again, green is 0 price movements. The red or orange that shows up there is a positive price movement, and the blue is a negative price movement.
I think that was
This one. Yeah. Who votes for this? Yeah. And who votes for this? Okay. Yeah, pretty much most people are voting for this. And those that are not voting are just staring at the pretty colors. Yeah, I mean, I would also prefer this, I think, because the problem is that the linear boundaries are really constraining you from being able to separate the space like that, for example. This makes a lot of sense that when you have no order flow, you get no price movements. And if you have positive order flow, you get positive price movements. But if imbalance is negative enough, it shifts it. Here, you get 0 price movements even if you have positive order flow and negative imbalance. Or even here, no matter where you move, if imbalance is slightly negative, you still get no price change, which is weird, right? And it's solely because this is not, these linear boundaries is not sufficient to classify this data. So you can't, this is a lesson to say, you can't just use classifiers naively and then just follow them, right? You always have to look at what is the output of your classification algorithm, and do they make sense? And since we're talking about financial data, do they make any financial sense? Can you attach a story to it? And if you can't, probably you shouldn't use it to trade. That would be my recommendation. Don't use stuff you don't understand to trade just because it's a really sophisticated machine learning algorithm that worked quote unquote on your data. It gave you results. You shouldn't just trust things because you shouldn't treat it like black boxes. So always go back and think about the results. Okay. So that's our little lightning taster view of classification. Next, I want to, where is it? Let's do, oh, yes, there it is. Let's talk a little bit about reinforcement learning now. So again, this is just a taster. So what's reinforcement? What's the idea behind reinforcement learning? So far, what we were talking about is looking at data, analyzing the data, without asking the question of what is it that I actually want to do with the data. So what do I mean by that second question? What I mean is, at the end of the day, you want to trade, right? In this context of algo trading, you want to set up trades. You want to act on the system. And then the system is going to respond to what you do somehow, and you want to optimize some performance criteria. That performance criteria could be maximizing profits while penalizing some measure of risk, and the output is, okay, when do I submit an order, when do I put limit orders in, when do I do whatever I do, how many trades to execute, et cetera. So that is actually the problem that you want to solve. Those other things are interesting and useful and important as ingredients into the actual more big picture of what the trading algorithm is going to do. Reinforcement learning tries to solve those optimization, those stochastic control optimization problems in an almost model-free manner. It doesn't do great when you use purely model-free approaches to things, but the approaches that are developed that are model-based are actually not even in tune with and aligned with how financial models are built. So one of the research agendas that I've recently started on is, in fact, trying to take these reinforcement learning algorithms and build into them the features that we actually see in financial data, and come up with more specific, kind of almost model-free, but model inspired, let's say, approaches to reinforcement learning. That research agenda is in the works, so we're not going to talk about it. I'm just going to show you some of the more basic reinforcement learning algorithms that are out there and show you how I think how I think it kind of fails on some data. Okay, so here's the setup. As I mentioned already, you're trying to maximize some sort of reward that the system is giving you as you act on it. And the system is stochastic in some manner, and you don't know what state it necessarily might be in, that there might be hidden stuff in there, and your actions affect the system. So you're trying to maximize a performance criteria that generically looks like this. You're taking an expected value, you're trading, let's say, out to infinity, and if there's a finite time horizon, you can modify this, it's not a problem. You take an action at a point in time that takes you from a state that you're in at that point in time into some new state. And that new state depends on the action you took, and the reward is a function of all three things, in principle. So you want to try to maximize that. So S, this is the set of the states, this is a set of admissible actions, and the system evolves in some manner like that depends on what the state was and what action you took. Okay? So this means distributed in some way. I'm being very, very vague about it on purpose, because the point is you don't want to actually model this. You want the observations of your actions and the world to update what you do. So this is another graphical model representation of what's going on. So you have the world evolving according to some states, which may or may not be visible to you. You have these states. This is the states that you keep track of, okay, which may not consist of everything in the universe. So you have this evolution. You take an action. That action affects the world. The world gives you a reward. Your reward also depends on what action you take. Think of it, there could be costs, for example, in there. The world also gives you stuff that you can observe, because there may be hidden things in here that you can't. So the world gives you stuff that you can observe. And of course, the observation may be affected by your action. And then the stuff that you can observe, you may not use all of it. You only use some subset. So this is the subset of things that you actually use. This is the set of all things that you could possibly have. This is the rewards that you get, and this is the action you take. And then this just repeats itself. Okay? And the goal is somehow to figure out how do I choose A optimally, given what I've observed and given the past history of what I've observed. So the main idea behind reinforcement learning is that you're trying to discover the action policy, by doing two things, what's called exploration and exploitation. It's like, imagine it's your first time in Rio and you don't know any restaurants, so you're going to try a whole bunch. Then after you've tried a bunch, maybe you got a recommendation as well, and you go there and then you reinforce, oh yeah, that was really good, so maybe you're going to go there more. And out of this bunch that you tried, maybe one was really good as well, so you might want to go back there. But you still will explore a little bit. Until you've known enough about the city and you know enough about all of the good restaurants, you're not going to explore anymore. You're only going to go to where's good. So this is the idea that goes behind reinforcement learning, is this trade-off between exploration when you don't know enough yet and exploitation when you do. Okay. So here's, actually let's, okay, sure. Let's spend let me check my time here. 12:30. Ah, yeah, okay, we're doing good, I think, yes? Okay, so this type of performance criteria, well, it's an infinite time horizon optimal control problem, actually, right, where I haven't really specified exactly what the dynamics on the system is. It's a discrete time optimal control problem because there's fixed points in time. So there is a Bellman principle that goes with this, which tells you that your value function can be written as maximizing over the action just at a point now that goes from the current state that you're in into some potential new state, plus the value function in the new state. Okay, so you can show that such a Bellman principle applies. And one way to try to figure out what the optimal actions are, if you knew the transition probabilities, so if I actually knew what the model was, if I knew that I can go from S to S prime when I take action A with this probability, then I simply need to solve that maximization over an expectation in a recursive manner. So one way to do it is you assume a policy, you compute you compute your reward. You assume an h function. You compute this sum over all possible states, get a new h function, put it back in, keep iterating back and forth, back and forth. You can show this eventually converges. And then the action that maximizes this term, the argmax, that is the optimal action to take at that point in space. This, of course, has a flaw. You need to know this transition matrix. We don't want to assume it. We don't want to assume we know what the transition matrix is. One potential way around is say, okay, let's just observe what happens. And as we observe, we just keep a record, like keep a little Q in mind of a probability transition matrix. Whenever we take an action, we just have different transition matrices. And we can keep updating them as data comes along and simultaneously trying to do this. That's one approach. But there's a better approach. And that's through this thing called Q-learning. So Q-learning is, they call it, actually I don't even quite remember why the letter Q was used, but here's what the letter Q means. It refers to the following thing. Define Q, which is a function of the point in state space and an action you take as the expected value of the reward you get by taking that action at that point in state space. And of course, you get into a new random point in state space, plus the value function at the new point in state space. But you can, of course, rewrite the value function at the new point in state space as the maximum of Q, because that is, in fact, this expectation that shows up here is Q. So the value function is just the maximum of this Q. So that's why I've replaced H with that. Now, you look at this equation, you say, oh, okay, this is actually also a fixed point equation. But it's a fixed point equation now, not just at points in state space. It's a fixed point equation for a function that's in state and in action. So it sounds like it's a harder problem. Right? We went from something where you only have a function of states to something where I now have to try to estimate something that's a function of states and actions. But it turns out that there's actually a very nice recursive way to estimate this from data without making assumptions on the transition matrix. And here's the idea. Actually, it's better to just go here. Here's the algorithm for it. And I'll show you why the algorithm makes sense, or at least give you the intuition. So you initialize that Q function to something that's random or often actually just 0. All zeros. You go to some point in state space. You go to your system, your real world. You're at a point in state space. You take what's called an epsilon greedy action. Now, what is an epsilon greedy action? It's simply this. It's this idea of exploring versus exploiting. You take a coin and you flip it. If it comes up heads, you take a random action. If it comes up tails, you take the best action or take the action that you think is best so far, based on your current estimate of Q. That coin flip, its probability of coming up heads decreases as time goes by, so that you start to explore less. You start more exploiting. Okay. So that's what we mean by epsilon greedy action. So then you've taken epsilon greedy action, you act on the system, so the system was in state S, you go to state S prime. You get a reward. So that's, you observe the S prime, you observe the reward. You update this Q function using this formula. Take your old Q, multiply it by 1 minus alpha, add alpha times the reward plus gamma times the maximum of Q at the new point in state space. So you have an estimate for Q already, so you can compute this maxima. Then you simply update your state, and you repeat. And you keep doing this until you've converged in some sense. Or you just constantly do it as you observe more and more data. There's a requirement on these alpha k's. They have to sum to infinity, but their sum of squares has to be finite. Okay. And so a typical choice is, in fact, these epsilon k's are usually taken to be something like that. Constant over constant plus k. And same thing with alpha. There are some other choices that are natural that show up and that seem to be produce good results in different scenarios. This methodology is used a lot in these kind of these robot game control things, where they try to train a computer to play Atari games, for example, or to balance something on a pole. So they've used variants of this type of methodology for that. Yeah?
Epsilon is like probability that you...
That's the greedy action guy, yeah.
So yeah, when you say epsilon greedy, it's the probability that you exploit versus...
Yes, probability that you explore versus, yeah. So epsilon is the probability of exploring.
And K is...
K is just the iteration, yeah, is time, yeah. K is time. Think of it as time. Okay, so why does this work? Okay, here's a simple intuition. Suppose I asked you to compute, okay, what is Q? Q is the expected value of something, right? Don't mind that it includes itself. It's the expected value of something. If I was to give you observations of a random variable and I said, estimate it, give me an estimator of the expectation. Well, what can you do? Well, you have all the observations, so you just do an empirical average, right? However, you can also compute it in an updating way, like this. So the estimator of some expectation is just 1 over k, sum of little x's. But I can also write that as take my previous estimate with one less data point and add 1 over k times the difference between the new observation and my previous estimate. This is the exact same formula. It's just written in a recursive manner. That mu k minus 1, well, if I put it together, that gives me 1 minus, let me erase that. If I put those two things together, I'll get 1 minus 1 over k, mu k minus 1, plus 1 over k, xk, right? That's what that formula tells me there. Okay, let's go back. 1 minus alpha k q, that is, mu is our q. It's our expected value we're estimating. What is x? X is the random variable. X is the reward plus gamma. Right? That is the random variable that I'm computing an expectation of. So it really does follow from this very simple observation. But you have to actually prove that it works, and there's I have some notes here on proving that this thing actually converges. Given our time, I don't want to bother with it. Okay, there's one more variant of the Q-learning that I think it's important to mention. This is something called Dyna-Q. So Dyna-Q stands for dynamic Q-learning, right? And the idea here is that you simultaneously have a loose sense of a model. Now, a model in this context doesn't mean some stochastic process or anything like that we're used to in financial math. Rather, it's simply the history of transitions from S to S prime that we've observed when we've taken some action A. You keep that Q, you keep that history of stuff. And that model, you revisit and use that model to update your Q function between actually acting on the real world. So in other words, you have a toy model that represents the empirical observation of what transitions you've observed. You run the update of the Q model, of the Q-learning on the toy model several times. Then you go to the real world, and you act on the real world. You get a new observation. You add this now into your model. And then you run Q-learning, updating on the toy model, go to the real world again, and come back. And this often converges faster and more stable. So here's the Dyna-Q algorithm. Okay, initialize state, select an epsilon greedy action, take an action, observe your new state and your reward, update your Q function according to the exact same rule as before. Now you update your model, so you add that transition into your model. You repeat this part a certain number of times. So this part says randomly select a state from where you've visited in the past. Randomly select an action that you've previously taken at that state. You get a particular reward because you know what reward you get when you take that action at that state. You've observed it. And now you update your Q using the exact same kind of formula, except it's from these fake It's from this toy model, from this fake action on the world. And then you just repeat this n times. Then you go and you update your system and come back again and act. Yep.
What is the criteria to update this n times?
Oh, how do you choose n? I don't think there's any theoretical work around what n should be. And practically, people just kind of try different values, like 10 or 100, and then stop it like that. Yeah, and the Q function becomes more stable because, you know, when you're particularly when you're first doing a lot of exploration, right? You're only getting these kind of random points that are updating your information that you have about Q. Well, there's information in those places that you've already visited, so you should use them more to smoothen out the updates of the Q function. That's basically what happens. Okay, so what do I have here? 2 simple examples of how this worked. So this was a toy model. Actually, both of these things are toy models. This was a toy model where I created a fake world that had mean reversion in the asset price. And I gave the agent that they're allowed to have up to +5 and -5 units of inventory. Whenever they act on the system, they would push the price in the direction that they traded, but not significantly. There's a chance that if I buy, then it's likely that the price is going to go up because I'm showing buy pressure in the market, so that should push the price up a little bit. And if I sell, it should push it down. But the prices also mean revert. The Q-learning algorithm doesn't know any of that. All it sees is the rewards that you get by taking the action, meaning the value of that trade. So I keep track of the book value of the shares. And then I just ran it many times. Excuse me. And this is the optimal policy that you get. So if you look at this here, this is the optimal policy as a function of my state of the worlds. So what states did I give it? I gave it the price change, the previous price change that occurred, and my inventory. That's the input. That's my state space here. That's S. So S was 2-dimensional here. What are the allowed actions that I can take? I can buy or sell up to 2 units of the asset. 0, 1, or 2. So what you see here is that when you're in this middle region, you basically do nothing. But if there was a positive price change, you tend to sell. And if you had a lot of inventory, you tend to sell a lot, right? -2. On this side, you tend to buy a lot if I saw a negative price change and if I had a short inventory, or I'll buy 1. So it's kind of learned that, oh, there's some kind of mean reversion going on in prices. To take advantage of it, when I see the price, if the price moved up, I should expect that it's going to go down. So I take an action that would be advantageous in that scenario. And this is a scatter plot showing you the green dots are all times at which the price moved up, and I've sort of scatter plotted it into here, and the red is all times the price moved down. So you can see there's more green in this area here, and more red in this area here, and it's mostly black in the middle. So whenever I have positive inventory and I see negative, sorry, when I have positive inventory, if I saw a positive price change, it's more likely that I sold. That makes sense. Again, it's doing exactly, it's another way to vision this picture. Okay, so that was one little application. Another application is doing an execution strategy. This one's a little bit harder to see. So what I've done here now, this is a finite time horizon problem. So the state space is actually 3-dimensional now. It's price, inventory, and the time remaining. Because once there's no more time remaining, then the game is up, right? You have to, it's like in those video game analogies, it's like when the character dies, right? And as well, if your inventory gets down to 0, your game is up. So what's shown here is, it's a little bit hard to see, but the state space is much larger, of course. This is time on this axis. This is inventory at price of 10.03, at 10, and at 9.97. And the colors are showing you what your strategy you you should use. What I'm trying to illustrate here is that this is actually quite noisy. These are the kinds of things that you get out of Q-learning. Because it's only exploring and then exploiting, and you're not visiting every single possible state in state space, and you're not assuming any structure in the underlying model, and you're not assuming any structure in neighboring points in terms of what's a structure in the optimal policy at neighboring points in your state space. There's no assumptions made there. So you definitely get noisy stuff. And that's one of the things that I'm I'm starting to look at, is putting down models within this reinforcement learning approach. There are model-based reinforcement learning approaches, but for the financial applications, they don't really make sense. They're not quite right. So there's a lot of other things that need to be done. One thing you can see, though, is, or hopefully you can see, this picture here is fixed inventory. This is the maximum inventory I have, and then I've just half and 1/4. You can see that you trade faster here when you have lots of inventory. That makes sense. And you trade slower as you have less inventory. As well, if you look at this carefully, unfortunately on this plot, price increases downwards. That's just the way that the image map generated it. And there's more trading, faster trading when your price goes down. Price goes up, because it's downwards on the plot. So that makes also sense, because there's a mean reversion in the prices here too. So if prices go up, then you should sell, because you expect the prices are going to come back down again. Okay, and that's a particular sample path. So, is that it? Yeah. All right. So I think that's the end of this reinforcement learning stuff. Little teaser. Any questions before I go into the last topic? Yes.
Is there any way in this algorithm there to force it that at the end time you have execute for sure a certain amount?
Yeah, that's what this is doing.
Okay.
That's how I've developed this particular application. You must guarantee that you end with 0. So here's an example plot of a strategy. So this was a sample path for the asset, and this is what the strategy did. So it ended eventually with 0, but most of the trading was done earlier on, and then because inventory is kind of low and the price isn't excessive, it kind of stayed here and then waited to the end, and then it got rid of it all. Yeah. But like I said, I think the strategy is too noisy. Right? The optimal policy looks way too noisy to me. Like, why is it that, at one cell, I'm going to sell 10, and then one little cell above, below, left, or right, it's 0. And then move over one more cell above, below, or 0, and then all of a sudden it's cell 13. It's too noisy. Yeah, but it was just as a toy example again. Okay, so the last topic I want to talk about, this is actually now cool, new, hot off the press research that we are writing the paper on. Yeah. And you're going to see how it ties into the machine learning stuff. It doesn't sound, the title doesn't make it sound like that. So mean field games and with, it should just say with, latent alpha, is the work that I'm doing with my current PhD student, Philip Casgrain. So, okay, we don't need to go about this intro stuff. Oh, by the way, yeah, we have a book on algo and high-frequency trading that if you're interested in the topic, check it out. There's a couple of other books as well. There's one by Olivier Guillon and Charles Lahal, editor. They look at the whole field in a slightly different way than us. All three are great. So if you're interested in this research agenda you want to pick up, I'd suggest you get all three of them. Okay, order flow. So let's not talk about this. Let's go straight to the latent alpha. So here is a kind of model-based approach that incorporates machine learning aspects into it. And you're going to see how that happens here. So I'm going to assume we have some price process that we observe, F, and the actual price process is S, sorry. F is kind of a fundamental price process. It's the price process in the absence of the impact of traders. So this here is the impact of traders. So that's what you actually observe. However, in this first part of the paper, you're the only one trading. So you're the only one who's affecting the price, I should say. So it's clearly wrong. I'll correct that afterwards. But for now, pretend that you're the only one affecting the prices. So your rate of trading pushes prices. If I buy, I'm going to push the price up. If I sell, so this is negative, I'll push the price down. I get to control my rate of trading, how fast I trade. This fundamental price can have 3 different components to it. There's a diffusion, so this is Brownian noise. Then there's a pure jump component to it, and I'll explain what the n plus and n minus are. And there's some sort of drift term. The latent aspect to things comes in the following way. This process A, we don't observe it exactly. We don't know it. We think, for example, that an example of this is that it's driven by a hidden Markov chain. And a nice toy example is to think of a price process which you've estimated somehow that it mean reverts to 2 different levels. There are periods in which it fluctuates around here, and then there are periods in which it fluctuates around here. Okay? So there's sort of 2 different price levels at which it mean reverts to. So this drift, A, T, could be, for example, kappa theta t minus ft. And theta t is either, either of these 2 values. This would be some value, say theta 1, little theta 1, and little theta 2. And this Markov chain theta can take on either of these 2 values. But you don't observe it. Okay? All you observe is the price itself. Alternatively, you can imagine that theta, that the parameter theta makes the process switch between being diffusion purely, so it's 0, or it mean reverts. So in other words, there could be periods of time in which the price process just fluctuates around, and then all of a sudden it switches and it starts to mean revert. But you don't know that. It's not part of the filtration that you adapt your strategy to. So this is a hidden Markov model, basically, that's driving that drift. As well, because we want to consider the situation where there are pure jumps in this process as well. Because some people don't like this drift and that diffusion. So you'd turn them off. And then you'd have a price process that's pure jumping. And that pure jump component has stochastic intensities which depend on the state of that Markov chain as well. So this is, again, latent-driven stochastic intensities. Within each state of the world, within each choice of theta, there may still be stochasticity in the intensities. It doesn't have to be a constant. The intensities could be stochastic, could incorporate Hawk's processes, for example, where there's self-excitations. However, there's an additional layer of uncertainty that's driven by this latent process. So we're going to have a trader who's going to try to optimize some performance criteria by observing S, having strategies that are adapted only to the filtration generated by S, or equivalently F, and somehow has to take into account the fact that there's this hidden stuff going on. So here's the optimization criteria. They're going to try to find the strategy that maximizes the expected value of the terminal wealth that they get from trading. They're going to penalize inventory at the end. So if you want to have no inventory by, say, the end of the trading day, this would be large. So you'd end with 0 at the end. And then there's some sort of running penalty. And this running inventory penalty prevents the trader from having 2 large positions at any one point in time. It can also be reinterpreted as model uncertainty. In fact, Ryan has a paper on the equivalence of this and an optimization problem where you have model uncertainty, where the agent doesn't actually know what the drift is, but has a reference model and then looks at a whole sequence of candidate models and penalizes them with relative entropy. And you can show that that's equivalent to having this kind of running penalty. So the key trick here is that nu is adapted to only the partial information F and not the full information G, which incorporates as well the state of theta. Okay? So it turns out we can solve this problem. I don't want to get into the details given the time, because I want to end a little bit earlier than 1:30. significantly earlier than 1:30 is where I want to end. But the key steps in deriving the results in this first version of the paper is to compute the posterior probability that the latent state is in a particular state, given the information that you have. And the key step in computing that probability is to introduce a new probability measure where the continuous part of your price process becomes a standard Brownian motion, and simultaneously the counting processes have a constant intensity, so one's a good choice. Okay? So you can show that such a probability measure exists in this context, and that this pi's turn out to satisfy some nice stochastic differential equation. Don't stare at it, okay? Just know that we can compute this posterior probability in an online fashion. So online means as we observe the data, okay? This is actually closely related to the hidden Markov model that we talked about before from the machine learning perspective. And I'll tie it in a little bit later. Another key ingredient, again, don't get bogged down by the math details here. Another key ingredient is that with this posterior probability computed, you can show that there exists two new types of processes, a new Brownian motion and a new jump process, which themselves are adapted to the filtration generated only by the price you see, and then they have particular properties. Okay? So the original processes, these W's and these N's, are not adapted to this reduced filtration. They're not adapted to the price filtration. Okay? But you can generate ones that are. That's what this says. Given that you can do such a thing, it turns out you can now recast this optimization problem, which is a partial information optimization problem, into a full information problem, where you have to add extra state variables. So you have to add these posterior probabilities as actual dynamic state variables into the system. When you do that, you can solve this problem. And the optimal strategy has a very beautiful form. It looks like this. You take your inventory and scale it by a function of time. This function of time is something called, well, the product there gives you a strategy called implementation shortfall. It basically will take, if you have some initial inventory, and if you only trade it according to this rule, your inventory will come down to zero in a sort of a nice concave manner. It'll do this. That's capital T. If this is your inventory, it'll just smoothly go down to zero, like that. That's what that first term would do. The second term is the really interesting term. The second term is where all of this latent information and hidden Markov model stuff gets buried. The second term is the expected value of the hat processes are your current estimate of what that drift is. So in this case here, you don't know theta, but you have a posterior probability of what theta being in state 1 or state 2 is. Right? We have a formula for it, right? That big SDE that I said, don't look at. Okay? So you have a formula for that. So you can compute the estimate of this A, which I call A hat. Similarly, you can compute an estimate of the lambda hat, and plus and minus. And if you compute this expected future value of your estimator and weight it, this tells me how to bias my trading strategy. Okay, in short, what does it say? In short, it says, if I expect, based on all the information that I currently have, that in the future the price is going to move up, I increase my trading speed. I buy more because I expect the price will move up. And if, on the other hand, this is negative, I expect the price is going to move down, I slow down my trading. Makes complete sense. Yes? Alpha was a terminal penalty to make sure that I end with zero inventory. So when I take this to infinity, I'm guaranteed I end up with nothing in inventory. I end up with lots of cash, but no inventory. Okay, so how does this, oh yeah, this is the example, numerical example. What I wanted to show is a case of a pure jump process that mean reverts. So you might think of, you can sort of think about how might you construct such a thing. Well, here's one way to do it. So n plus, n minus are counting processes. They jump. The lambda plus intensity of n plus is a plus kappa times theta minus s and the positive part of it, while the jump intensity for n minus is a plus kappa theta minus s, the negative part of it. So of course, the difference between these two things is exactly that. So it looks like a mean reverting process in average, in expectation, right? That's how processes get pushed. So, and theta is some Markov chain. Turns out that we can, of course, compute this thing analytically and estimate it. This is not a great plot, but the next one is a little bit better, but let me explain what's going on here. This is many sample paths drawn where we've forced the process to first mean revert to some level that I think was 5.05, and then forced it to mean revert to some level that was 4.9, I guess. Okay. However, the trader didn't know that. The trader knew of the levels. They don't know what level they're mean reverting to now. The trader also made the wrong assumption about how active you switch between the two mean reversion levels are. So they thought that the thing was switching fast, but here it only switched once in an hour. We made the trader think that it's going to switch 10 times in that hour. So this is a bad scenario for the trader. However, we still find this here showing the heat map of the posterior of the two estimators. So it correctly predicted that it's going to be most likely in the up regime early on and then switch to the down regime later. This is the heat map of the inventory through time. It takes on a short position, then unwinds and becomes slightly more aggressive on the buy side. And here's the P&L from that entire strategy. Actually, I think it was in 99.9% of the scenarios, it didn't lose money. Now, this is cheating, right? Because I am generating data from a model that I know, but I don't know what the levels are. So I'm hiding information, but I am generating from the same, but I am running scenarios on the same data generating process. I'm just making it not switch as fast. I'm giving it a bad scenario, but it's still, so that's great that it's doing well, but you should, of course, not take this as, oh, okay, great, let's run this strategy and we're going to guarantee profits, right? And never shortfall. But it's an illustration of how that works. Okay, let me tie this in to the HMM stuff from before. Because I didn't say anything about where did I get these parameters, or do they make any sense, and so on. Calibration. How do we take this model, which is, the mathematics behind this is all continuous time optimal stochastic control with partial information. That's techniques used to solve it. But then to actually run it and use it in reality, you need to tie it back to some data. And that requires now recasting the model as a discrete time hidden Markov model. So these thetas are in the background that we don't know, right? That's our data generating, that's our hidden Markov model that modulates the world. The prices are what we observe. The difference between this and the HMM that we studied earlier is that there was no connection between the visible layer before. Here we actually have connection between visible layer because previous price definitely affects what the next price is going to be. It's not simply conditioned on some hidden state. Okay? That extra addition actually makes it no longer a standard HMM. You have to rederive everything in this scenario. So you can go ahead and, again, write down, similarly to before, this completed data log likelihood. And you can find a way of maximizing the parameters. It turns out now we don't simply have an emission. Before we had just an emission probability from the hidden state to the visible. Because we have this connection here, and our data is generated by a process that is not simply discrete distribution, right, for the emissions, you now have a difficulty in optimizing that part of the completed data log likelihood. However, it turns out that there are efficient ways to do it using GPUs, which is what we did. There's a similar forward-backward type algorithm that you can develop for this. Those are the update rules. Again, forget details. Let's look at some examples, data. This is Intel for all of January 2014 between 10 a.m. and 11 a.m. We've made the starting price always 0, so we subtract the initial price. Those are the sample paths. Doesn't look like much of anything. It looks like kind of Brownian noise, right? However, if you calibrate this to that two-state model where you have not A being this, but the intensity, it's the pure jump model that we're calibrating here, you find that these are the set of parameters. So the hidden Markov chain is relatively sticky, right? It likes to live in regime 1 or regime 2 whenever it's there. It's most likely that it always starts the day in regime 1. And in regime 1, you don't have very much mean reversion. It's kind of small. Regime 2 and the activity is a little bit low, and the mean reversion level is positive. This is in ticks. In regime 2, on the other hand, okay, you do have double, or yeah, about basically double the mean reversion rate, and you mean revert to a negative level, and activity is much higher. So this is an interesting thing to see that you can't tell just by looking at this. You actually have to run the calibration procedure to see that you get that. If you do 3 states, you see even more refinement in here. So this is the least active regime, and you mean revert to something that's positive. This is the next most active regime, and you actually you pretty much don't mean revert in this regime at all. This is pretty much Brownian motion. And in the third regime, the most active regime, you do mean revert fairly strongly, but again, to a negative level. Other interesting things you can do is look at the joint co-integrated pure jump model. So you can think about that. How do you get a model that generates data that's co-integrated, but there's pure jumps because you live on a grid? We didn't see any such model written down anywhere, so we use the same framework, but a multivariate extension to it. And this is looking at Intel and SMH, and you can see, again, it's hard to tell anything there, but if you put them on day by day next to each other and set the initial price to 0, you do actually see some sort of codependence between them. And then if you run the calibration procedure, we have 2 regimes again. We're doing this, and you'll notice that in regime 1, there's not really any codependence between the 2 assets. So they're kind of moving like Brownian motions on their own and not correlated in any way or co-integrated in any way. However, in the second regime, they do become fairly strongly co-integrated. So this is illustrating the fact that, yes, these things do have some co-integration features, but it depends on this latent state that's around there. Based on all that calibration, you can then run the type of analysis that I showed before. Okay, but this is what's behind it. Okay, last little taster. As I mentioned, we were ignoring the actions of all other traders in the previous analysis. We said that we were the only one that affected prices. But actually, of course, there's a sea of traders out there. Everyone is affecting prices. So what we were curious about, we have a couple of papers related to this action of multiple agents out there. But we wanted to look at how does the action of multiple traders get affected by this latent state process and generalize it and using completely different approaches for solving the problem. So here, we're looking at a whole bunch of agents that have trading rates nu1 up to nu-n. The agent strategies are adapted to this filtration generated just by this F process, right, which is the same as before. So F is kind of like the unaffected price process. S is the true one. So S has a stochastic drift, which is latent. So it's predictable on some larger filtration. We do not have access to G. We have access to the filtration generated by F, and that's a subfiltration of G. But we have also the action of all other agents here. and M is some martingale. We don't have to specify it. Okay, so the first little thing that we do is show something similar to before. We can find some sort of filtered version of the processes such that there is a martingale that is adapted to the reduced filtration, that is square integrable, and the price process can be rewritten in terms of that. And this A hat, actually there's, yeah, that's F, good, so this is correct. So that the F dynamics can be written in terms of an F predictable manner, as opposed to here, where it's written in terms of a G predictable manner. A is our filtered drift. It's the analog of exactly all that machine learning machinery that we had before. So hiding behind this expectation is all of that HMM and estimation and so on. Okay, so here's the problem that all of these agents are trying to solve. Each agent has a strategy that they're trading. So if they're selling, I think this was a selling, actually this wasn't, yeah, this was a selling problem, I guess. They get worse than the mid price. They're affected by their own rate of trading. They have a penalty on their own inventory, and then they have their terminal value here. But of course, this S process that shows up here and here is affected by all agents. So everyone is affecting your price, not just you. So this problem is too hard to solve, so we're going to simplify it by taking the infinite number of player limit. So we have all of these agents here, and they're all interacting and affecting each other. So you have this mesh of stuff going on. What we're going to do is we're going to say, the strategy is this. We're going to say, let's suppose that all of the agents average, their average action, follows a mean field new bar. We're going to go to the ith agent, one arbitrary guy here, and say, okay, this ith agent sees a mean field from all of these other guys. I'm going to optimize, the ith agent is going to optimize their trading strategy against this exogenous mean field. Then that's going to give them an optimal strategy, which depends on that mean field. However, if I average over my optimal strategy, it should be consistent with that mean field. There should be a fixed point on the space of controls. And that, if I can solve that fixed point, then I've solved the mean field problem, the infinite player problem. Then, the finite player game, they're going to apply that mean field solution in the finite player game, and you can show things like what are called epsilon Nash equilibria, that if they follow such a strategy, they can only improve on it by an amount epsilon, and epsilon goes to 0 as the number of players goes to infinity. Okay? We're not going to go through all of that. I'm just going to show you again, just tasters of what the idea is. So, as I said, we're going to take some mean field, and we're going to assume that it's some F predictable process. We're going to do this through a completely different approach that's normally done in any of these mean field game stuff. We're going to use a convex analysis approach to things. So first thing is you'll notice that this performance criteria is actually you have to show that this is in fact a convex function on the space of controls. Turns out that it is. Then you can apply this machinery from convex analysis, which says, first of all, try to find the equivalent of the first order condition. That is, find the Gateau derivative in some arbitrary direction omega, and find the strategy which makes the 0 for all possible choices of omega. So it turns out that this is Gateau differentiable. Its Gateau derivative has this form, and notice that there's an iterated expectation here where the inner expectation is conditioned on the filtration that you know. The outer expectation is, conditional on the filtration that you know at time little t. Okay? And turns out these are necessary and sufficient conditions. We can show that this Gateau derivative vanishes for every single admissible direction in our control space if it satisfies a forward-backward stochastic differential equation of this type. So if you don't know much about FBSDs, don't worry. It's just some stochastic differential equation you solve backwards. And as a corollary, because of this fact that we can show that it is sufficient and necessary, that if we find the strategy that actually, if we solve this FBSDE, that truly is the optimum of our control problem. Turns out that we can, in fact, do this not just for the uniform heterogeneous agent case. We can solve this problem where there's subpopulations of different types. So imagine that there's a whole bunch of players of type 1, a whole bunch of players of type 2, a whole bunch of players of type 3. Then, using the same methodology, we can show that you end up with the fixed point problem for a vector of mean fields corresponding to the mean field for every subpopulation. And they satisfy a vector FBSD. And this is what it is. It doesn't matter in particular. What's really cool is we can actually solve this thing, closed form. And the solution has this form. The solution looks like the mean field is some deterministic function of time times the mean field inventory plus some stochastic process. And that stochastic process has a very interesting form. It is an integral of, think of this as a matrix, a deterministic function of time that's a matrix, multiplied by the expected value of our latent process. Very similar flavor to what we had before. I don't know if you remember the strategy. Let me flip back. There. See, this is the expected value of that times a deterministic function of time. What we have now for the subpopulation case is instead a deterministic matrix function of time times this expected value. This is one of the first times, actually it's the second time that I've seen time-ordered exponentials showing up in algo trading problems. It also shows up in another paper that we did, but it's unusual that it does. The ith agent has a really cool decomposition. The ith agent strategy is follow the mean field, but correct it by some function of time by an amount that's proportional to your distance to the mean field inventory. So if you're away from the mean field, you're going to try to trade toward it. There's no way, we didn't set that up as a criteria for the agents. This is just what's optimal. This is what will give them a Nash equilibria for the mean field game and an epsilon Nash equilibria for the finite player game. Here's an example of the simulation. So we've done the same background model. So there's some sort of pure jump process that is mean reverting to one level or mean reverting to another level. We've done all the same kind of filtering stuff that we did before, but now layered into the mean field game setup. And here's a particular sample path. We're showing the difference between the affected and unaffected price. This is the filter along that particular path that we have, and you can see it correctly picks it out. And here we have 10 agents trading, and this is their inventory, and you can see they're moving around in a stochastic manner, adapting themselves to what they believe the price is going to be doing, and they eventually kind of converge to the mean field. The difference between the dotted line and the black line is the black line is the mean field, the dotted line is the empirical average. So, of course, the mean field, we initially assume that the agents have zero inventory on average, and so there's a discrepancy between the true empirical average and the mean field. And of course, as n goes to infinity, that will go to 0. So that's kind of this epsilon error that you see showing up. But they eventually converge. Okay, I think with that, I'm going to say thanks for your attention. Hopefully you saw lots of interesting new things, and you all want to do algorithmic trading now.
Well,
anyway.
Thank you very much, Sebastian. It was a very nice course. Very, very nice. So perhaps we have time for one quick question now. And if people want to talk to Sebastian later, perhaps during or after lunchtime, we have now a good 1 hour and a half break, and more or less. So any quick questions, but objective, please.
Yeah, Antonio.
The question on this, for example, the classification problem.
Yep.
If supposedly usually when you calibrate the model,
Yes.
take like the futures, like suppose if plus 1 second or lag of a time.
Ah, okay, yes. Mhm.
It doesn't matter exactly the exact problem, but the problem is how about calibrate the classification when supposedly you have like correlation between the variable that you want to predict. Supposedly that you don't use a difference of mean price of 1 second. You use like a difference of price of a longer period, but you're going to move the variable in second. Do you understand the difference?
I think so. So you're saying, so the question is, what if, yeah, the question is, what if the features that you're using in the classification are not somehow independent of one another, right? So you're saying, for example, if I have, look at the price change between time 0 and 10, and then I go from time 1 to 11,
Yeah, exactly.
and then 2 to 12.
Features you move exactly.
Yeah. I think you can still naively apply the methodology, but it does break some of the underlying assumptions, right, in there. I don't know what theoretically would go wrong, but you can certainly apply it and see if you get anything that makes sense out of it. I don't know. Maybe there's some other classification experts here that can speak to that effect, but I think it probably would be okay as long as there's not too strong. Yeah, yeah. Good question to think about.
Okay. Well, let's thank Sebastian again.